Hello and welcome to Office Hours with Bill Jennings from Klamath Community College. Today, I'm making a video for you on solving other types of equations. This is going to be a series. This is the first video in a series. And the first one is going to be about higher degree polynomial equations. What I want to talk about real quickly here is this strategies to be successful in our college algebra course. What we need to be able to do is identify a type of equation. Each type of equation is going to have a set strategy for solving it. Linear equations, easily identifiable as something, an example here, 2x plus 5 equals -7. The goal there is to isolate the x, get all the numbers on the other side, divide out the coefficient, and everything goes away nice and clean. We've moved to more complicated equations than that. Linear equations is the only one where we're going to be working on isolating the x. What we're going to do with these polynomials of high degree, our strategy is going to be all about getting everything on one side and setting it equal to 0 and finding a way to factor it so we can use that zero product principle. Or we might be able to use the quadratic formula, and maybe along the way we recognize it as something we could complete the square against and things would go very quickly there. But this polynomial is going to have these very specific strategies. We need to be able to identify polynomials. A quadratic is a type of polynomial. Here's a cubic equation. That's a polynomial. And there's a fourth degree equation. Those are all polynomials. And that strategy is going to be all about setting it equal to 0 and hope for the best. So that's our step number 1. Set this equation equal to 0. Then we're going to factor it. Now the problems that are set up here are going to be very nice. They're going to factor well for us. Later on in the course and later on in your studies, what you're going to learn about is ways that you can use synthetic division to start factoring things out when it isn't quite so easy to factor it. But these ones are going to factor by methods that we probably have known, usually like the formula for perfect cubes and also for factoring by grouping. So, and then we'll be able to use the zero product principle. So and then we'll use the zero product principle, set each factor equal to 0, just like we did with the quadratics. That would be set there. But we're going to use examples here that are going to be higher level than a quadratic. So we're very good at solving quadratic equations now. Those have their own set of strategies. Now we have something that's a higher degree. So remember, step number 1, always set equal to 0. See what we really have. So I need to get this stuff on that side of the equal sign over to the other. So I started with a 9y squared. This 18y squared needs to go to the other side. So I'm going to have to subtract 18y squared from both sides. That 4y is going to have to move, so I get a minus 4y. The plus 8 was there, and set it equal to 0. And how I really pulled that off was simply subtracting 4y from this side, subtracting 18y squared from that side, and it moved over to the other side as such. Now, it says the next step is to factor. Well, I'm hoping that this will factor. Now, this set is kind of really tailor-made for the techniques we already know. If you see something that is this should have been a 3 here, sorry. That's a 3 there. If we see something that's set up and like this, we need to be able to take and say, okay, well, it has more than 3 terms. I sure hope this goes factoring by grouping. That's all we know so far. If we didn't know that, we'd have to kind of start stabbing at it, and hopefully something synthetically divides. That comes later on in the course. Let's look at this pair here and hope that there's something in common there. And there is. A 9y squared that's in common, leaving me with a y minus 2. Now on the back end, as you know, for factor by grouping, I've got to end up with something that matches, otherwise it won't work. So hopefully on the back something matches up. So there's a -4 that's in common here. And if I factor a -4 out, I'll get a y minus 2. Remember that if you distribute that -4 back, you'd have to create this. And that -4 coming out is really important because this is only going to work if that y minus 2 and y minus 2 match. That's how factor by grouping works. So I still am not done factoring because I got to finish this factoring job up. So let's go ahead and do that. So a y minus 2 was in common in both, and then I've got a 9y squared minus 4 equals 0. Well, this can be factored one more step. I've got a y minus 2, and then I've got a 3y minus 2 and a 3y plus 2. Recognize this as difference of two squares. and then I'm able to factor it very quickly. Now, I have it in a factored state, and it says here, set each factor equal to 0. So let's do it. Y minus 2 equals 0, 3y minus 2 equals 0, 3y plus 2 equals 0. At the end of the day, y equals 2. Now on this one, I'm going to add 2 to both sides, and then I'll divide by 3. Take your time with it if you need more time, but it will end up being 2/3, and this one will end up being a negative 2/3, because when I subtract 2 on this one, I'll add 2 on that one, and then divide by 3. So here is my answer. I end up with 3 answers. We could make it look nice and clean and pretty if I do a negative 2/3, 2/3, and 2, and put it in my solution set notation, and there we have our solution. So we were able to solve a polynomial of 3rd degree by factoring. Very nice that it did factor by grouping. Now let's go ahead and apply this strategy to this next problem that I have lined out for us. So this last problem I have lined up for us on this example, again, if it's 3x to the 4th equals 81x, I'm really stuck in the dark unless I'm going to use this 0. I've got to get it factorable, and the whole idea behind factoring is I've got to have it as something times something equals 0, and then I know each of those somethings is going to make a 0 out of it. So let's go ahead and move everybody over. So this is 3x to the 4th minus 81x equals 0. Let's see if we can factor that. Well, it looks like I'm kind of stuck, but always think greatest common factor first. I see a 3 and an 81, and I see something in common. I see an x to the 4th and an x. So I think I can pull a 3x out of that, leaving me with x to the 3rd minus 27 equals 0. Now, I really kind of have it in factored state, and I could set each one equal to 0, but I can just keep factoring along the way, and maybe I'll be okay. So this is 3x. Now, we need to be able to recognize this as a difference of cubes. This guy just kind of sneaks up and grabs us every now and then. This is actually going to factor out to be x minus 3, and then I'll have an x squared plus 3x plus 9 by my formula. The little tricks there was the SOAP. It's the same sign, opposite sign, and always positive. This was a minus sign, so that stays minus. This is now the opposite of that. It was minus, so it's the opposite of that sign. That's the O of the SOAP. And then the always positive, regardless of whatever happens, this back's can always be positive. And this x came from the root, or the 3rd root of that, and the 3rd root of that, and everything. You should have seen this someplace before. Now, I'm still factoring away. If this was factorable, it would sure be nice to continue to factor, but I've never met a perfect cube a difference of cubes that ever produced something that would be factorable here. And so, but the good news is it's a quadratic, and we know how to solve quadratics. And how we solve quadratics that we don't know how to factor, we could complete the square against it if we're looking for some extra work, or I could just simply use the quadratic formula to finish this up. So let's go ahead and set each factor equal to 0. I've got a 3x that's its own factor, so 3x equals 0, which really just implies that, hey, x equals 0 is one of the solutions. I could plug that up here, and I could actually kind of look at it and say, hey, if x is 0, 3 times 0 equals 81 times 0. That's going to be one of the truths of solving this equation. Certainly going to work. X minus 3 equals 0. I'm getting the x minus 3 as being this factor here. Well, that's going to imply that x equals 3. Well, if I go back up here to the top, I'd say 3 times, this would be 3. And well, 3 to the 4th is 81 times 3 is going to be a really large number. But over here, this is just going to become 81 times 3. So it obviously checks, and we're all good to go there. Now, I'm going to take this last factor, which is this one right here, and that's going to be x squared plus 3x plus 9 equals 0. Like I said, it'd be nice if it factors, but it doesn't. But the good news is I recognize it as a quadratic, and I can see that a equals 1, b equals 3, c equals 9, and it's now time to plug it into that quadratic formula that we've memorized. So x equals a negative 3 plus or minus the square root of b squared, which is 3 squared, minus 4 times ac, which is 1, and a 9, all over 2 times a, which in this case is a 1. Now it's just a matter of running with it. I'm expecting that my discriminant, the b squared minus 4ac, otherwise known as this right here, is not going to come out to be one of those really cool numbers that we've talked about in the past, because otherwise it would have factored. So I'm expecting either an irrational answer or an imaginary answer, and looking at this, I've got a feeling I'm going to get an imaginary answer out of this, which is okay. Plus or minus the square root of, this is going to become 9 minus, what do we have here, 36 all over 2. I can continue simplifying this out. Negative 3 plus or minus. This is going to be the square root of a negative 25 all over 2. So this is a negative 3 plus or minus 5i all over 2. Now, the thing to note here is that all polynomials or higher degree equations will have a number of answers that is relative to, well, I could have looked at it here in a more standard form. If it's to the 4th degree, there'll be 4 answers. Sometimes you get the same answer twice, but at the end I should have 4 distinct different, and when I say, not say different, but sometimes I get the same one, but I should be able to find 4 answers in my work. I had x equals 0, that was one of my answers. I had x equals 3, that's one of my answers. And this right here represents 2 answers because I have a negative 3 plus 5i over 2 and a negative 3 minus 5i over 2. And I could write that out as a negative 3 plus 5i over 2 and a negative 3 minus 5i over 2 to show all 4 of my answers. Thanks for watching. There's more videos in the series on these multiple different types of solving equations.